and the channel length and the equalization delay are initialized, and we have randomized the channel parameters. So LMS channel can work for any random channel. So we have normalized that, and I'm generating a QPSK transmitted sequence with a random number, and which is also complex. This transmitted sequence is passed through a channel filter. So after it passes through the channel filter, it gets distorted. That is represented by X here. And I'm also adding a noise here, complex noise, and normalizing it. So the input to the receiver now basically consists of the output from the channel filter in addition with the noise. It is represented here, X equal to X plus 1. So now I'm discarding the starting samples which are used for the channel smoothing, and they're represented by K, and capital X here is used for transposing the input vector, that is used for the multiplication. So here comes the main algorithm, adaptive LMS equalizer. I've taken E as error and initialized it, and I've taken C as the channel weight, mu is the step size. So y equal to 1 to t minus 10, which basically represents the training part. The error is calculated by, by the difference between the transmitted sequence, that is the original sequence, and the output of the equalizer. The output of the equalizer is basically the product of the channel weight and the input vector. So the error which is calculated in this stage is used for updating the channel weight here. So as I mentioned in the slide, the same formula is used here. The channel weight is updated by the product of the error function and the input vector. And after this process is repeated for the total training samples, the final optimal channel weights are obtained. And now the symbol is detected, and I have calculated it by the product of the input vector. So here comes the original symbol that I'm going to display. And I'm also calculating the symbol error rate, which represents the error in the symbols compared to the total length of the symbols. So I've taken the symbol and I have calculated the error for the symbol using this equation by calculating the difference between the original and the calculated symbol and the transmitted sequence. And I'm calculating the SER by those symbols whose error is not zero divided by the total length of the symbol. So this basically represents the symbol error rate, and I have displayed the input symbol, the transmitted symbol, equalize symbol, and the convergence, which I'm showing it now. So I'm running it now in MATLAB. So and I'm running it in MATLAB. I've got this graph. So the value 0.0023 basically represents the symbol error rate, and the input symbols are clear as dots here on the left side of the graph, and the right side of the graph here represents the distortion caused by the channel, and this is the transmitted symbol, and after equalization it gets like this. So this transmitted symbol is converted into a similar fashion as the input symbols. So we can now see the error rate here compared with the number of training samples. So first the error is very high, and as the number of iterations goes on, it just decreases to a normal value. So this is the LMS algorithm, and now we'll see about the RLS algorithm. The initial conditions are the same for the RLS algorithm also. We have taken the 3000 samples for data and the 2000 training samples, the channel length, and those are all the same. And after the channel is passed through it, and after the signal is passed through the channel, it is passed through this RLS equalizer, which I'm explaining it here. Error. is initialized and the channel weights are initialized. Here I am using a set of parameters to calculate the update in the channel weight. So here R inverse, it represents the correlation matrix, and here I'm initializing it to a value. I of some function basically represents an n cross n matrix. That means L plus 1 cross L plus 1 matrix. So during the training phase, I'm calculating the error, which is basically the difference between the transmitted sequence and the output of the equalizer, which is the channel weight multiplied by the input sequence. And here the set of parameters are calculated at each interval. These parameters are described in the project code. That is, the R inverse is multiplied by the input vector, and these three processes are repeated to obtain the gain constant. And this gain constant is multiplied with the filtered input vector to obtain a value which is going to be multiplied with the error function to obtain the updated channel weight. So this value is multiplied here with the error function, and this is used for updating the channel weights. And R inverse also is modified at each iteration. So this process repeats for the T training samples. After the training sample is over, the symbol is retained, and SER, that is the symbol error rate, is also calculated in the similar fashion as the LMS algorithm, and the resulting graphs are plotted, and it can be now shown here. So this is the graph obtained for the RLS algorithm. This is the input symbols and transmitted symbols, same as before, and this is the RLS equalized symbols. And as you can see, the difference from the LMS and RLS here is that the error signal has fallen very rapidly, whereas in the LMS algorithm, it took some time to get down. So that means, as I've said before, this is due to because of the fast convergence that's happening here. And now let's get to the last algorithm, which is CMA algorithm. The initial conditions are same. The one thing to remind here is that channel. I have not selected a random channel here, same as before, because CMA algorithm is very sensitive to channel conditions. Because of the multimodal property, it can choose any minimum that is possible, and it can greatly affect the performance. So I've initialized the proper channel condition for getting an accurate output, and I've normalized it, and I've sent the transmitted sequence, mixed it with noise, and then the channel update that is happening here. And here I have used R2, that is a constant envelope, which is used for calculating the mean square error. It is 2 for QPSK symbols. I use in a step size of 0.001. So there is no training here. It just undergoes the whole iteration for the whole data samples. So the error here is calculated by the absolute square difference between the output of the equalizer and the constant modulus, which is 2, and the channel is updated as shown in the slides by multiplying the error function with the output of the equalizer. So, and after the training sequence is over, the symbol is calculated here, and the symbol error rate is also displayed here, same as before, and the output is obtained like this. So this is the transmitted symbol. Because we have used a different channel, the transmitted symbol is different, and after equalization, the output is like this, and the error signal falls over the iterations in this pattern. As you can see, the error rate is very high in the beginning, and it is not falling very rapidly. This shows that it has less convergence speed compared to RLS and LMS. Now, based on these results, uh, I'm going to analyze the conclusions and the results. So, so I've taken this is the other form of the results, that is for the LMS, RLS, and the CMA. And now, what I have analyzed from these results is that The recursive least square algorithm has high convergence and accuracy, which is then followed by the LMS algorithm and CMA. Because RLS algorithm is based upon the least square approach, which is based on the cumulative errors of all the previous errors. So it basically is the time average of all the errors. And the LMS algorithm is just the statistical average of an error at a particular point. So so it takes a lot of time to converge compared to RLS, and the accuracy is a little less than the RLS. When it comes to CMA, the convergence is high than LMS and RLS, and accuracy is also poor because it does not require training. There's a good side to it. So these are the downsides to it. And which equalizer to choose for for a system? It totally depends on the three factors. I mean, what cost are you willing to afford to it, and what convergence and accuracy do you require for the system? If the convergence and accuracy can be compromised, then we can definitely use CMA because it relieves us from the burden of transmission overhead of the training. And if you can spend a little on the cost, then RLS is a very good choice because it provides high speed and it is very accurate. And LMS, it is simple and it is reasonably accurate. It goes in the middle way. So the application areas where RLS algorithms are used is space communications because it will provide a very high accuracy. That's the reason for choosing it. And the LMS algorithms are used in military applications because it has a reasonably good accuracy and it are also moderate in cost. CMA, due to its unique channel initialization conditions, it is used only for specific purposes because the accuracy is also not up to the mark. So it is mainly basically used for civil purposes like users, like normal people talking on the phone. So yeah, thank you everyone.